Yes. Okay. So I want to reveal a topic that will involve mean value theorems, but let's start through a problem. Okay. Let me not mention the topic and such. Start. Sorry. Let me start with a problem. So this is a limit problem. Okay. A limit problem. 1 minute. Yeah, there is some problem. Okay. Yeah, so let's start with this limit problem. So here we have given that limit of, so here first of all, sorry, we have a function f that is from R to R, just the usual R to R. Now it is given that limit as x becomes very large, fx plus f prime x. So f is differentiable, it's assumed. This limit is given to exist. Okay, given this limit exists, or let me just make it more concrete, 0. Show, or I can just say, let's keep it show that limit fx x tends to infinity also exists, and find it. Okay, so let's give ourselves a minute and think about this. If someone knows it, tell us a few hints. Okay, that will be good. Don't tell the solution in one go. Okay. So we will be using this problem to discuss some theory. Okay, but let us first do this problem. I remember this one. It's not that difficult, but this was in one of the tests in BSc first year in CMI. I remember, but it's not a difficult question at all. I have a side question. Can anybody define? This may not be very important for this question, but it's important in general. Define this thing. Limit extends to infinity. Any function that exists. What does this mean? Because usually limits are defined for, when we are trying to go near some point on the number line and we're trying to define the limit. This also intuitively, I suppose all of us understand, but anyways, we'll say that if not, that's not the case. Can anybody define this? Yes.
Can you write that f dash x as f of x by x?
F dash x as f of x by x. Why?
Because if you apply L'Hospital rule, then
F of x by x. So you're saying in this limit, you want to replace. Okay, let's see. Okay, what is the reason for this?
if you apply L'Hospital rule, backwards.
No, I don't understand. So you are applying L'Hospital rule on fx by x. but you don't know. Yeah. So let me write this. This was the point of discussing this. That's right. So let me write this clearly. Applying L'Hopital.
Sir, I applied, I thought we should apply f of x is equal to e to the power of x by in e to the power of x into f of x by e to the power of x.
Okay, so that will come to that also. But let's see let's see if there's anything wrong with this. Applying L'Hopital on this gives f dash x. But why is this not correct to do in this case?
Sir, because it's changing the function.
Sir, we don't know if it is 0 by 0 form or
Changing the function is not a problem, but if we don't know if this is in, yeah, that is something that can be said. Yeah, we don't know if fx goes to infinity or fx goes to 0. But more than that, there is a more, or we don't know, rather I should say, we don't know about f dash x. We will state the L'Hopital's rule clearly, but intuitively we all understand. It's roughly we all, should just say roughly, we all understand. The main thing is that we don't know if limit f dash x exists. That will be the precise way to say, right? See, if you know that limit f dash x exists, then you can apply L'Hopital's rule, right? This should exist if you want to isolate it. Yeah. So we do not, I'm not writing this. We do not know if limit f dash x exists. So we cannot apply the L'Hopital's rule in this way. Okay. So it's basically like you are breaking the limit and you're writing limit this, but then you're already assuming limit fx exists. Okay, so that was one thing. These are the small things I'm discussing, otherwise problem is not that. Okay, let's come to the second thing. So yes, so maybe Raghav, you had an idea.
Sir, I just suggested that we write f of x is equal to power of x by e.
Okay. Okay. Right. Okay. Cancel or something. Okay. Yeah. Also, if okay, so these are two things. Maybe we can do this first, and later on we can define this. It's not very important for this problem, but anyone has picked up a little on this. This seems like a good step. Okay, yeah, so tell us. Okay, limit x tends to infinity, f of x. So yeah, I mean, you can assume that the numerator is, let's say, I'm just doing it a little formally, hx or gx hx, and the denominator is gx, right? And now you have to check that hx h dash x by g dash x is equal to fx plus this, right? And this limit exists, right? Limit h dash x that's given to us, right? Yeah. So limit hx by gx also exists, and it is also equal to 0. Yeah, is this correct? Does everybody think this is correct? Okay, why? Hmm.
So we don't know anything about f of x. I mean, how can we apply it to that?
Right. So let's go into the statement of the L'Hopital rule, right? Hmm. In the original limit. No, but that will be the same thing. That is just, yeah. No. So what is the L'Hopital rule? So suppose you want to calculate limit x tends to infinity fx. Suppose this is what we want to calculate and also figure out if it exists or not. Okay, but then if, yeah, okay, go on. Right, okay, yes. F of x, yeah, plus f dash x. Mm-hmm. Just on g dash x? On g dash x? Uh, or do you want to divide by e to the power x? Okay, so just if you, yeah, let me change the, yes. Okay, so what can you say? No, how do you know? How do we know? It, I think it does exist, but how do we know? No, but you have e to the power x also, right? No, but you have e to the power x also. Isn't that, is that not going to change?
So I think he's trying to say that you can separate.
No, you cannot separate. Yeah, that's right. You cannot separate. You can just take some simple example, right? I mean, you can take this to be uh, 1 by x plus say 1 by x square or something minus its derivative. No, e to the power x will override that, right? So you cannot do that. But you, what you can do, basically this will be the same as what we have done here. You can just divide by e to the power x, right? You can divide by e to the power x. Now you can write this as a derivative of e to the power x, but that goes to the same solution, right? Yeah, so you cannot separate, right? Unless you know that both the limits exist in the product, you cannot separate, right? Obviously, in some conditions they can, but mostly you cannot. In general, you cannot. No. So here, what does L'Hopital say? That limit fx by gx extends to infinity if you want to investigate. If limit x tends to, if limit x tends to infinity, f dash x by g dash x exists. Sorry. If this limit exists, then limit fx by gx also exists. First, let's think about this. Right? What is the limit? You know that, sorry, it will be equal. But do you agree with this? This is the crucial part of L'Hopital's rule. If the limit of the ratio of the derivatives exist, then it implies that the limit of the original thing also exists. That is usually given. Yeah, that's also given in the. Yes. Okay. Yeah, but so what you're saying, if fx is equal to minus x, in that case we get this. So why can't we apply L'Hopital here? Yeah, but then it is already 0, so it's fine. But you cannot apply. Yeah, but that's right. But the point, his point still stands. 1 minute. No. Yeah, both. But it's right that before you apply the L'Hopital's rule, both the numerator and the denominator should either go to infinity or both should go to 0. In this case, we know that this goes to infinity, but this, yeah, that's before you can apply that, that's needed. But no, you're right. Yeah, but in the proof, I don't think that's needed. Anyways, let's come to the, so what you were saying about applying by this method. Why is this better? Because, but it has the same. No, why? Because here also you have the same problem, right? Gx by e to the power x. Yeah, but we don't know again if it goes to infinity or not. I mean, we don't know if gx goes to infinity or not. It will be the same problem. Hmm. Okay, so then yes, you're right. Yeah. So maybe one has to do that, but I think that is not. One more. Let's just think about that. So let us erase these things. So that can be done independently. In fact, once I think in the class only we had this problem. Other people were there that time, and that time we actually proved that it exists, because that time it didn't strike to any of us to use this trick. But I don't want to go into that now, proving that this limit exists. Okay. Yeah. So the point is, see, if you can prove that limit fx exists, then you are done, because in that case you can apply L'Hopital's rule, right? So if limit fx exists, then we are done, because then this quantity will go to infinity, and so there will be no problem. Yeah, so let's just give 2 minutes to us, and otherwise uh, we will see later on if this limit exists or not. Okay, or maybe uh, the problem only says to find the limit and not to prove.
That is the problem. The limit of f of x.
Yes. So let's think about that. No. So maybe the problem is incomplete. Maybe you need some more condition to say that the limit of x exists, right? So I may be misreading because I'm just doing this from memory, the problem. So let me just think about this for a minute, because it may be that limit fx exists is not true, and if it is true, then this is everything is happening. So yeah, let's just wait for a minute. No, I don't think this is correct. You cannot prove that the limit exists. You have to assume it. Yeah. So the problem.
Sir, can we go by some epsilon data definition?
No. I know. I'm saying that it is not true that the limit of fx will exist. You will have to assume it in the hypothesis. Assume also limit exists, and then just find it. Because it's not true. So now the task is, and again, I think this is true. Okay. I think that you cannot prove this. You can try to find counter examples. Okay. So find example. So just find an example of a function f for which the limit does not exist. So find, example where this limit does not exist, but limit f dash x plus fx is equal to 0. Okay. Yeah. So try to do this for homework. I think this is the right thing. So this limit becomes 0, but limit of fx doesn't exist. So it means that limit of f dash x will also not exist, right? Means if one of them exists, other does not exist, then the limit of the sum cannot exist. And so some kind of an oscillating. So basically it will be some kind of a, so as a hint, you can take like some kind of a badly oscillating function. Okay. But the oscillations of fx cancel the oscillations of f dash x. And so together when you add them, they become a good function and the limit exists. Okay. But but the limit of fx doesn't exist. Okay. So there will be oscillations, but the oscillations of f will cancel that of f dash x and so on. And so that will exist, but limit of x. Yeah. So that will be the thing. Okay. But you see, we have still used so, okay, first of all, is this problem clear then? Right? What we have to do? Okay. All right. But you see, we have still used L'Hopital's in a very fine way, in the sense that the trick part is okay. That is just trying to see an expression as a derivative of something and so on. But we have to look at the L'Hopital's rule very carefully here. Okay. Just existence of limit of f dashed by g dashed implies that limit of fx by gx exists. Okay, this is the part of L'Hopital's rule that one must not forget, that it also implies the existence, obviously provided that it's in a 0 by 0 form or so on. So let us state the L'Hopital's rule clearly. So if so let's fix C. Let's do it with the notation. So let me write here. Let's do this. Okay. So C. Now C could be in reals or it could also be infinite. Okay. Now if limit f dash x by g dash x x goes to C exists, and limit, I'm sorry, limit fx by, no, not limit fx, and if both f and g go to infinity or both go to 0 as x goes to C, then limit fx by gx C also exists, and it is equal to, now this is the boring part, but I'm just writing it so that I do my thing, that yeah, this is a clear statement. Okay, are there any questions? Okay, so then here is my question. This is a slightly, let's see, it's not a problem. The question is, can, so this thing, if limit x tends to infinity fx by gs exists, then can L'Hopital's rule be applied? So is this thing true in general, that whenever the limit exists, can L'Hopital's rule always be applied, or are there any legal obstructions to that? So this is a conceptual question. Yeah, so there is no problem in the existence. I'm telling you that the limit exists. Then can L'Hopital's rule be applied?
I don't think so. So, for example, if you take function
Mm-hmm.
sin of x over x
Sine of x over x, yeah.
and tends as x goes to infinity,
Uh-huh.
I think that this will become 0 as sin of x.
Surely.
Limits in 0 by 0 or infinity by infinity form, but still the limit exists.
That's right.
Its derivative is cosine of x over 1.
Right.
Take the limit say this x tends to infinity, and I don't think that integral gets
Yeah, this does not even exist. Right. Does not exist. Right. it does not even exist. So you see, the derivative controls the function more than the function controls the derivative in some sense. Right? If you know about the derivative, then you can say about the function, but knowing about the function doesn't tell you about the derivative. Okay, like it is along similar lines, or it's a similar kind of statement that the derivative being zero strictly, if the derivative is strictly bigger than zero, it means that f is strictly increasing. Is that right? We know this, right? But the converse is not true. Okay, you can again, you can try to think about this. Okay, you can note these small things down or whatever, but you can think about this, not hard. Okay, so these are the things. And also we will see it in other places. Like if you have a certain chord on the graph of a function, then you take the slope of this chord. Any chord you take its slope. You will find a derivative which has that slope. But given any slope of the, or given any like tangent, I should say, with a slope, if there is no, there might not be any chord of that slope of that tangent, corresponding to that slope of that tangent. Okay. So basically, the whole idea of mean value theorems is to comment on the function from its derivatives, right? And this is again a similar type of statement, comment on the function using the derivatives, but the reverse might not be true. Okay. Right. Right. So let me remove this. So we have seen L'Hopital's rule from different angles now. This one we understand. Okay. All right. So here is the thing then, okay? In general, limit fx by gx extends to c may not exist, right? Or limit, this limit may not exist, right? What I'm trying to say is that one of them might exist, but the other might not exist. This might also happen, right? Okay. Okay, let's remove this question. So we will explore this situation more now, but before that, I think we can just do a proof of this theorem, right? And then we can explore the situation. Yeah, so let's take some time and think about a proof. Think, because we already have the ingredients to prove it from the previous classes. So let's think about a proof. So assume that all the hypothesis holds. How would you, from the limit of this, help? How will the limit of f dash x by g dash x help you to show that limit of fx by gx exists? How? Think about this. We'll prove this and then we'll move on. Right. So any ideas? We have seen these kind of expressions, at least you can guide yourself. Hmm.
They use CMVT.
Okay, so you Cauchy mean value theorem. Okay, so how do you use it?
Like Cauchy mean value theorem states like that if there are function is if there is a closed interval and the function and two functions are continuous and differentiable, that closed interval that f of a considered any 2 points in that interval f of a minus f of b over g of a minus g of 2 equals some g prime of alpha over g prime of alpha where alpha belongs to that interval. So
Right.
we can
Mm-hmm.
we have to divide like in that expression
Mm-hmm.
f prime of first we should write Cauchy's mean value and after that take limit on both the sides. But we can do that f of a minus f of b divide by a. So we divide and multiply by a. So it will kind of become like some of
Mm-hmm.
you familiar to LMVT.
So you're saying I'll take this expression and divide by a minus b.
And also multiply by a.
I mean, both numerator and denominator you'll divide.
To keep the expression the same. If you separate the terms out carefully, then it will look like an expression for LMVT.
Okay.
So can we proceed from
LMVT, how will going to LMVT help? Yeah, how will I, so going to LMVT will not help. You need to somehow bring this into the picture. Yes, yes. Yeah, we're obviously assuming that, right? F and G are differentiable. Otherwise, F dash x by G dash x. Yeah, so F and G are differentiable. So for the moment, let us assume that C is equal to 0. This is just for simplification, but we will see that you can reduce the other cases to this more or less. Means you can reduce them. So let's assume, now this is the way to deal with these things, right? These are general functions, you can transform and so on. Assume that x is 0 for a minute and try. And also assume that fx and gx both go to 0 as x goes to 0. So again, see the hypothesis again. Yeah, this limit f dash x by g dash x extends to 0 exists, and both the functions go to 0 as x goes to 0. Okay. Now we want to basically show that this limit also exists. Fx by gx, so we can forget about all this. Let's also remove this for the time. So the Cauchy mean value theorem is what connects the slopes to the derivatives. We had seen that this is actually also the slope of some kind of two variable function, but let's not go into that now. That can help you to give a geometric picture of L'Hopital's rule, but for the time being, let's keep it simple and try to prove this. So now the hypothesis is simpler. You can also assume that fx is, let me just make this minus 1 to 1, though again, it doesn't matter, but just to make it very, for some reason, yeah. So the problem that is happening maybe for you guys, I don't know, is that there are in the Cauchy value theorem statement, there are two things, FA and FB. But in this, there is only F by G. There is no minus or any other thing. So how do you deal with that? You have to think. Okay, let me make another assumption. Okay, this is just to make the problem easier. Okay, we can remove those assumptions one by one, but just to make the problem easier, let's make this assumption further. Further assume that f of 0 is equal to g of 0. Okay, now see, this might be an extra assumption because we don't even know if f and g are defined at 0. In the, yes.
I think so. Then technically, there are two variables. So, like, if can we write f of x over g of x as f of x minus f of a plus f of a, or g of x minus g of a plus g of
Separate. What is A? Some arbitrary A? Arbitrary A may not be a good thing to do. Anyways, let's see. Let's see. What do you do from here? Ah, no, I see, no. Yeah. But you can keep this idea because it might. But now already, you see, we are focused around the point 0 and we have assumed that f of 0 is equal to g of 0 equal to 0. This is an assumption that we are making to make this problem simpler. Okay. In the original problem, maybe this assumption is not there because f and g need not even be defined at 0. Because we're talking about, that's why, that's the reason why maybe you look for limit fx at 0 because f is not defined at 0. But now this will give a clear way, right? You have f of 0, you have fx, you are interested around 0. You can get this kind of an expression because now it is the same thing. I'm just not doing anything basically. This is the same thing, just exactly same. Now what?
this will be equal to some f prime of alpha by g prime.
Yes, right? Sorry, this is 0. Okay, so let me not say limit. Let me just say this expression, okay? Because we don't even know if the limit exists. Fx by gx equals to this. Now this is equal to f prime alpha. Okay.
Now we take the limit of both the states and we
Mhm. Sorry, g of 0 will be 1 if you take e to the power x. No, no, no. But no, no. But there the limit was towards infinity, right? So it would be infinity in that case, right? But we are only focused at x tends to 0, and I am assuming that both go to 0. Okay, I'm assuming a simpler case. So the more general case, like infinity case, you can replace as a hint, you can replace x by 1 by x. You can consider a function like that. Instead of fx, you can take 1 by fx. You can see you can make those adjustments and improve the other cases. But we're kind of bringing it down to the simple case. Okay, now here, yeah, let's just think about it again, what it means to take limit on both sides here. Mhm. E to the power x into fx by g of x, like this. Okay. Mm-hmm. But this is not h dash. Okay, yeah, this is h dash. No, this is not h dash text though. Why am I writing equal? No, no, this thing is not h dash text, right? This thing is differentiating the. Mm-hmm. Yes, yes. Plus derivative of right. Okay. Okay. How? No, how can we claim that? No, but that does not mean that the limit will exist, right? And even if that limit exists, you don't know if this limit exists. You need to know that the limit of the ratio of the derivatives exist, right? To apply a L'Hopital's rule, right? Just existence of the limit does not mean you can apply a L'Hopital's rule. Right. These are the subtle points. Okay, so I'll just bring my charger from some other place. You guys just think about completing the proof. I'll just come and do it. So just take your time, think. If you have any questions, ask them. Okay, I'll come in a minute. Okay, so let's clear things and then some of you can say, is everybody following? Okay, everybody, those who have not said much today, so I don't know, it's online class. So, okay, let's remove this also. Let's remove the statement of mean value theorem also. Okay, so what should we do from here? But
So no, but alpha is a fixed.
as x changes, it also right. So we can just write alpha x. Okay. Okay. So if you say take limit x tends to 0 on both the sides, can you justify why this is okay? Because we don't know if both the sides. No, that doesn't have to be 0. Why should that be 0? No, that, I mean, but then it's fine. Then it will be infinite. Yeah, then the limit can be infinite, right? I mean, we know that this limit exists, right? We know that RHS, the RHS, I mean, the limit on the RHS exists. And that's all we care. That's the hypothesis. Is that okay with everyone? Yeah. Limit x goes to 0 implies that alpha x also goes to 0, right? And we know that this limit exists because as x goes to 0, this limit exists, right? So this is the special part of that, right? Alpha x may not cover all x around 0 or something like that, right? But just write this formally, x goes to 0 implies alpha x goes to 0. So limit uh, exists implies this limit also exists. And both are equal. See, that's also important, right? Right? Because alpha x also basically goes to 0. Okay, now you can use the definitions of things and prove it. It's not difficult. If you want, you can prove it. Otherwise, it intuitively makes sense, right? Because suppose you want to show the limit of this is L. You want to show the limit of the RHS is L, right? And then you take an epsilon and then you want a delta. Just pick the delta that you use here. The same delta will work there because alpha x will even be closer to 0, right? I'm not saying the details. If you're uncomfortable with definitions of limits, try to prove this. See, this looks intuitively correct, but different people may be comfortable with limits at different levels. So try to prove this. Like actually use the definitions and prove, because we have done the epsilon delta definitions. And if you're not comfortable with that, then if you don't know the epsilon delta definition, then you can leave it for the time being. We will revisit that in a different cycle. But this is important to know. for various reasons we will see. Here, obviously, you can understand this is equal to this limit only. And so we are done. Okay. But simultaneously, do people see that existence of the limit? Okay. What I'm trying to say is that limit fx by gx exists does not imply limit f dash x by g dash x exists. Does not imply. And we've even seen a counterexample, right? But let me just mention that again, and let's try to see it conceptually through a proof, because seeing things conceptually through a proof can tell you a lot about the nature of the kind of counterexamples. Sometimes counterexamples may be difficult to come up, but you can see it directly. Let me first write it. So limit, we have already said this, but through the proof, you can actually see, okay, it doesn't have to happen. The counterexample is not surprising. This exists does not imply that limit f dash x by g dash x exists. Can anybody explain that conceptually? Or can anybody point out conceptually how that can be seen in the last few lines that we have done? There is a lot of merit in seeing it like this, because then you will be able to come up with sufficient conditions under which this does imply the right hand side. Counter examples may not tell you that, but now you can come up with sufficient, you can add, once you can point it out, once you can see it in the proof, you will know, okay, I need to add some more conditions. Few more conditions are thrown in, then it will imply, because in good situations, it does imply. So let's try to see that in the proof. First, let's try to see what is making it fail, what exactly is making it fail, and then you can remove that delicately. So maybe today I'll go up to 11 or something, okay? Is that fine with everyone? Everyone. It's supposed to be 1 hour, but I'll just go a little longer today. Either way, I'll record it so you can see it in case you have school and stuff. On where? Here? Okay. Okay. Why? No, that we are already assuming that fx does go to 0. Yes, here. No, here also you can assume that a limit of f and g both go to 0. So here also you can assume that limit f and g go, you can assume everything good. even then, yeah, you can differentiate, but I'm saying that if you don't put it in the hypothesis, if you do not assume from beforehand that this limit of f dash x by g dash x exists, if you don't assume this, then it will not be implied by limit fx by gx existing. Yeah. So I'm saying that limit fx by gx might exist and everything might be good, but still you cannot differentiate. Or yeah, that I'm right. Yeah, still you cannot differentiate because we don't know if this limit exists. And I'm trying to say that that is there in the right. So what am I saying again is that the limit of the ratio of the derivatives existing does imply the limit of the ratio exists, but the converse is not true. And you can see that in the proof. See, in this one, okay, let's write it. If LHS exists, right, that implies that RHS exists. Okay, but then why does that not imply that limit f dash x by g dash x exists? It does not, right? Because alpha x by alpha x might be a special subpart, right? So basically the reverse, limit x tends to 0, f dash dash alpha x is something that just goes to 0 as x goes to 0. It kind of stays ahead of x in the journey to 0, but still the point is that alpha x might jump. This exists. Does not imply, I mean, this is a bit, the flavor is like, limit along a specific sequence exists, but the limit of the function does not exist, right? But this does not imply that limit fx by gx okay. And obviously, even with the condition that x is bigger than alpha x. Okay? So essentially, see, this is not a question about this. You can just replace this thing by h also. Just some, basically my point is just this. I mean, this is derivative only. Yeah. This existing does not imply this limit existing does not imply that this limit exists, limit of h. Limit of h of alpha x existing as x goes to 0 does not imply limit of h exists. Okay, because alpha x may not check, right, all the values. So if you are at 0, I mean, you have not at 0, but around make an interval. Suppose you choose an x here, right? You choose an x here. Let's say you get an alpha x here. And then you choose a smaller x, you get a smaller alpha x. But this alpha x also goes to 0 as x goes to 0. But alpha x may be a discrete set, right? It may just jump values. It may be like of the form 1 by n or something like that. Do you guys see the point? Right? So for example, it could be the case that alpha x is equal to 1 by, no, 1 minute. Alpha x could be, once again, you take 1, you take x, So you take 1 minute. Yeah, alpha x could be something like this. Right, I mean, something which is, less than x, right? But it is always like of the form 1 by n or something, or maybe the ceiling will work, something like that. You see, I mean, let's check it. 1 by x is bigger than this. And so what happened? No, I should take the ceiling, right? Yeah. Take the ceiling. So the upper thing. So you see 1 by x is less than ceiling, right? But then when you invert it, you get that this is less than x. So you see this is less than x, right? But this is a special sequence. I mean, it's always 1 by n form, right? It's always 1 by n form, right? But then what do you get? Just to explain this point. Then what does this kind of thing mean? This kind of thing basically then just means that this exists, right? At best, this is what it means, right? 1 by n, because alpha x is only 1 by n, taking the values 1 by n type. Even maybe worse than that it could be. But in the best case also, it's something like that. In the best case, for this particular example, in the best case, alpha x is just like this, 1 by n. It cannot check for more than things, for things other than 1 by n form. Right, so this limit exists. Obviously, this does not imply that, I mean, in general, right, h of 1 by n goes to infinity. This obviously does not imply that limit of hx as x goes to 0. The converse is obviously true, but obviously this is not true, because just knowing along 1 by n doesn't tell you the whole thing. So is this fine? Yeah, just take a minute, just take 2 minutes and think about this, and then ask me questions. Okay, so anyone has questions? Any questions? Very simple questions, especially better, right? Because clear the basics, honestly check if you understand things, go through it. No, the function can be differentiable. You see this function h, this function, but the point is that function may be differentiable, but f dash may not be differentiable. Right. And so we don't know. But even if f dash is differentiable, in that case, you have asked good. I think that makes a lot of sense. Because alpha x cannot be constant, right? And so let's come to that. That's what I was saying by now we can add some small conditions. And obviously these will be given to you as problems, if this is continuously differentiable, then show that converse of L'Hopital is also true, or something they will say. but we are kind of trying to discover that in some sense with a little bit of by asking the right questions, basically. Yeah, so let's come to that. So this is all okay. You can go through it again later and ask, but right now let's move to this. Yeah, now the point is that if f dashed and g dashed are different, are just continuous, right? If they are continuous, no, even then we can't say that f dashed by g dashed. Yeah, but then so then I think this is someone else was saying if g dashed is not 0 and limit g dashed x goes to 0. These are some extra things we are doing, okay? Just that's it's basically more maybe interesting things. The limit x goes to 0, g dash x is not 0, right? Then obviously we know that this is also continuous, right? And then the limit will exist, right? That implies this exists. Okay. And then if it exists, then it has to be equal to this. There is no problem, right? Because if we know that the limit of something exists, then you can find it via any sequence, like alpha x. Right? So if limit x goes to 0 hx exists, then you can find it using any. These are the tricks we use to find limits and so on, right? We basically intuitively also we think, okay, let me take x equal to 1 by n and see what is happening. Or let me take two different sequences. If I get different limits, then I can say it doesn't exist and so on, right? We're basically using the same thing, that if the limit exists, then you can traverse along any path, basically. Sequences are like paths on the number line, different kinds of ways to jump to it, to 0. So limit x goes to 0 hx exists, then now this is just all of us. If someone doesn't know this, you can ask, because I've not discussed these things with everyone. But we are doing this in a different place where we are starting this topic. Anyways, this, and then infinity h of 1 by n exists, and obviously they will be equal. This is n, right? Or for any sequence, you can take any xn, any xn that goes to 0. So basically, if you go to 0 by x, if you go to 0 in general and the limit exists, then you can go to 0 by any sequence, and xn goes to 0 and tends to infinity. Xn goes to 0, I'm just writing it there. Usually it's not written there, but point is, yeah. Okay, so if the limit exists, if you somehow can know from a different means that they exist, then they will all be equal and so on. So this can be used to frame more difficult questions, where they can ask you to calculate a limit of some complicated things like this, where it is f dashed by something something using the limit of fx and some converse of L'Hopital like. So you need to remember on this. The idea is you must understand how you analyze this, so on. So are there any questions? Yes,
We have to generalize that.
we have to generalize. That's right. Yeah, we should generalize. Right. So what you're saying normally? Sorry.
Normally, questions like in many of the questions, this may not be
Yes, yeah. So how do you generalize? Yeah, so basically you know that, let's say, assume this at least, that limit f and limit g as x goes to 0 is 0. Okay, now see, it is not, now there is no problem here in assuming, yeah, 1 minute. Okay, so if, wait, someone's mic is on. Okay, okay, no problem. Yeah, so what was I saying? Yeah, so see, if the limit x, yeah, but in a lot of places they assume that f of 0 is 0 and g of 0 is 0. Okay, but if it is not given, then what can you do? So if it is not given, I mean, if f and g, sorry, right, 0 comma x, then right, no, but how do you know that the limit is 0? Limit of fa is 0. Limit of f when, no, so we have to, no, uh-huh, no, but fa may not vanish when a goes to 0. We okay, yeah, right. No, so sorry, you're right. I think you are taking, hmm. But then you're going to take two limits. Let's write it. So you have fx by fa and you have gx ga. Then you're going to take limit a going to 0. Is that right? Okay. And x is fixed here. So then this will become this. And then you want to take limit of x goes to 0. Yeah, this is very nice idea. Yeah, and here you would have got some f dash alpha. That's, yeah, that is, okay. Here you will get f dashed alpha. In this case, the alpha will be between x and a. No, but the problem is then this alpha may not go to 0. No, it will go to 0 because x is going to 0. Right. Yeah, so this is a good reason. This is a very good, straightforward reason. Right. But I was just saying that, look, if you are trying to calculate the limit at 0, right, then the value of the function at 0 does not really matter. Does it matter? No, right? So you can just simply assume that f of 0 is 0. I mean, so it could be like f at 0 is not defined, right? If it is not defined, you just define it to be 0. And if it is defined to be some a, I can just again define a new function, right? Because value is f of 0 has nothing to do with the limit as x tends to 0. It has nothing to do with the limit as x tends to 0, right? And I think that's what your proof is also showing, more or less. It does not matter, right? F of 0 has nothing to do with limit. So this has no relation, right? This has no relation, no relation with this. So this is just for convenience, right? Or you can, if you want to be very rigorous, you can just say that, look, instead of considering the function fx, I can just consider the function fx minus f of 0. I can take this as my new f. And you can do various things. And by using any of the ideas, you can do. And the other things, like what happens if f goes to infinity, you can take 1 by f, and you can make similar transformations to do the other cases. Okay. All right. So this was okay. Now let us actually go to. So we have seen that. So we have seen that limit fx by gx. Let's come to the basic case. In the case that we prove, because that case is enough to get other cases. We have shown that this does not imply. I'm just saying this in the sense that existing. This does not imply this, but this implies this. Okay. Now, these kind of results are there in plenty in maths, at least even if you just come down to analysis. Okay. Root test, ratio test, they all have this kind of things where one of them less than one implies the other is less than one, but that doesn't imply, in various places. But the point is that, look, these two things may not exist. One of it may exist, the other may not exist. Okay. But what can we still say in the situation when they are not existing or when they are not equal? Okay. Let's come to this. If fx by gx does not exist. Okay. I mean, the limit. And this is where it really becomes interesting. Let's say that as you go to 0, this limit does not exist. Or let's say in general, a limit x, some function hx does not exist. Okay. Why are we exploring this case? Because see, if you look at the proof, the limits actually came later. We have a priori, we always fundamentally, the Cauchy mean value theorem always gives us a relation between a function and its derivatives. Yeah, regardless of any limits existing or not existing, we still have an equation. The limit was a very imprecisation of this equation. It's like the geometric progression formula for finite n is much more complicated, right, than the infinite case. That is just taking into infinity. But there's a lot more enriching thing in just this equation, which suggests that we can explore this situation further even when the limit does not exist. Okay. Just as an example, I will give you, or intuitively, if you would like to understand. Yeah, first. Suppose you are around, suppose you want to understand fx by gx as x goes to 0. Okay. A limit you're not able to take, let's say limit does not exist. But this equation still has a lot of things. Okay. Suppose limit you're not able to understand, but let's say you can still take something like minimum. Now this is another kind of C. Limit is just a way to understand something at a point where the precise answer does not exist. Right, just like sequence at infinity, we don't know what it is, but we can still understand its nature at infinity by one number like L, the limit. That more or less tells you what the sequence does when x goes to infinity, up to any error you want and so on. Okay, so here this concept of limit is too tight, it's too strong, and it doesn't exist, let's say. Then I can say, okay, let me see if I can calculate something called a minimum. I mean, not something, you know what it is. No, I was meaning something. I should actually say infimum and so on, but let's keep it minimum. Okay, you cannot understand, or you don't, the limit concept. So limit is just a concept to capture it, right? At f of at 0. Let's say that concept is too strong, not working. We have to play with something simpler, some simpler way to understand. So minimum is maybe another way, though it's not a good way, but this can be made precise. Let's say you take the minimum in a very small ball, not even one. I will just say small delta. I'm just saying small. Eventually, I'll have to take delta to be 0, tending to 0, but minimum of this quantity. I'm trying to understand minimum of this quantity when x is in a sort of small ball around 0. Maybe you can remove the point 0 because that's where you don't know. If you knew it, then more or less you don't need to do anything. Well, no, that's a wrong statement. Sorry. This is what it is, let's say, for the time being. So do you guys agree this is like, if limit is a very profound thing to understand the nature, limit is a very powerful thing. It's just one number that tells you so much. The limit of a sequence is that one number tells you about that infinitely many terms. If you're willing to let go of finitely many for an act, for knowing about the thing towards infinity and so on. Obviously, there's a trade-off that will always be. But let's say you want to understand this thing. Okay, now this is a very unprofound thing. This is a very naive kind of thing, but still, in a small ball, if you can understand the minimum, it's not a bad thing. Okay, minimum may not exist, but let's say it exists. Okay, for the minute. Otherwise, you have to take infimum, but that concept, maybe not all of us are very comfortable. So eventually, we'll bring that in, but now let us. So we can also take it for this thing. Now you guys tell me, which one is going to be bigger? Can we say anything? Oh, wait. What am I? Why am I writing alpha x? Alpha x is just what we get, but fundamentally we want to understand between these two things, right? Fundamental question is this: can you say which one is bigger or not bigger? I mean, roughly speaking. So this equation you can try to use. Mm. Yes, right. That's right.
Just calculate equality
Mm-hmm. Mm-hmm. Yes. Alpha x is lesser than x. This is a maybe you can use. And this is a fundamental question. This is this kind of question taking minimum over a smaller. Think about this. Let's see. The idea is that this is a coarser way to understand the nature at 0. A very coarse way. A coarser option. Limits. Limit was very fine. It doesn't exist. Now we are going for coarser options. So this has nothing to do with calculus or more or less. This is just a set theory question now. I mean, there is no action going on now. It is just everything is there. You have to just say which one is bigger. Okay. I'll just say the answer and you guys think about it. It is not difficult. Maybe we can, no, maybe we can just discuss this because my answer may not be correct. Because I'm just trying to do this in a certain way. Usually this will just be introduced directly as something called lim-inf and so on. But that will not sound very interesting and you will just forget it after some time. Maybe. See, the point is that whenever you're taking this something here, right? You are actually, whenever you are evaluating f of x by g of x for some x inside this, you're basically picking something from here only because of this equation. Right? Whenever you want to fx by gx, you're basically picking something from alpha x, picking something from the second set only. Right? So it's like the left-hand side set is a subset of the right-hand side set. So its minimum should obviously be bigger. Can be equal also. Is that okay? Right? I mean, alpha x is just a subset of x. Right? All possible alpha x's in the neighborhood delta to minus delta is a subset. I mean, you can just replace this by this. This becomes a subset, right? Now it's clear. That's all it was. Okay. Yes, that's right. Because alpha x is less than x and bigger than minus x because it's positive. We know that. And similarly, that side also, negative side also. Yeah, so that was that. So basically, yeah, that was important, and both are important, both the equation and yeah. So this is the thing. I mean, when your results about equality and things are coming from equations will usually tell you more. So even when you loosen your notion of limits and so on, this might still hold in weaker senses. But more is true, much more. Now, for those who have done the theory of sequences, this will be more, I mean, at least when the way I did it, then this following, which I'll say is more, you can relate it. but I'll say it in a way that, let's see. See, when the limit of something, some hx at s goes to 0 does not exist, then what do we aim? What can we do? We can look at all possible limits. How do you define this? I don't know. There are many ways, many different ways, many non-equivalent ways to define all possible limits. But intuitively, you can think of this as, I mean, where all can the function go as x goes to 0? Or just take all possible sequences towards 0 and calculate the limits, possible limits. So you get different limits, right? This is just informal, right? You get different limits. You can look at all possible limits. Now, this is something that we do, right? We look at the limit points of a sequence. All of you may have not done that. But you can understand, just take a sequence. There may be several sinks to that sequence, right? Intuitively. But let's not go more into that. You can look at all possible limits. Now, when we do this, we know that the set of limits of a set, or the set of limits of a sequence, or the set of limits of a function at a particular point, that set is no ordinary set. There will always be a biggest limit and a smallest limit, because limit of limit is a limit. Even if you don't believe, you can just believe that there will be a biggest and smallest limit. Because the supremum of limits is also a limit of the limits, but then that will also be a limit of the function. So the supremum is also a limit. Intuitively, this is okay. So the biggest limit and the smallest limit, they have notations, but let's just call this L, and let's call this L of h, of the function h. Okay, so the way we have proved this minimum is bigger than this minimum, in the same way you can prove when you define it, or when the definition is given to you, or if you have to build a theory, you have to define it. You have to write if you figure out some intuition and you want to write something on it, you have to formulate your own definition. Like I just made a definition of minimum to discuss this, to avoid the limb swap thing and discuss this in a simple, intuitive way. I just framed it right now. Just let's say just to a minimum. But in the same way, you can show, as you have shown this, you can show that the smallest limit of f by g will be bigger. And this is not even very surprising now, because of this equation. Right? Because of this equation, the smallest limit, we have not defined it. Okay, but you can understand, right? You go close to 0, but you just keep picking the smallest possible values. So it's like you pick the smallest value in this neighborhood, and then you let delta also go to 0. So you take a neighborhood, take the smallest value, take a smaller neighborhood, take the smallest value, take a smaller neighborhood, take the smallest. These will have a limit. Okay, or you can just say, I'll take all possible limits and take the smallest limit. Just like we have proved that the minimum of this is bigger than minimum of the right hand side, smallest limit, when it is properly defined, will also be like this. And the same proof will work. Like the proof will be exactly the same. Only maybe you will take a few minutes more, or maybe more than that, to get comfortable with the definition. The definition is a little, it depends on how much you have seen this. But then this is obviously believable, and this is like in the word phrase itself, otherwise phrase will be wrong. Smallest limit of anything is obviously less than or equal to. It can be equal also. When will it be equal? When will the smallest limit of anything be equal to its biggest limit of anything? When the limit exists. Yeah, continuous is a special case of that, right? So smallest limit is equal to biggest limit, right? For anything, and this is just obvious, right? Smallest limit should be equal to biggest limit means that there is only one limit. And if there is only one limit, it means that smallest limit is bigger than is equal to biggest limit. Right. So this lim_inf and lim_sup, which are smallest and biggest, what is called, they are equal if and only if there is a unique limit, which means when the limit exists. So this will also become a generalization of what we have done of the L'Hopital's rule. And now this symmetrically, just like we showed, the minimum of fx by gx is bigger than the minimum of this, the supremum or the maximum will be less because you're taking the maximum over a smaller set. Just like taking minimum over a smaller set increases the minimum, taking maximum over a smaller set obviously decreases the maximum, right? So this will be less than biggest limit of this. This is actually what L'Hopital's rule should be, even when the limits don't exist. Because L'Hopital's rule is not about the limit, it's about Cauchy mean value theorem. I mean, it says this is a geometric phenomena, which we have already know of a parameterized curve. Okay. Now, once I give you the definitions, which maybe will not do, because that will just be technical, not needed now, and we can give it in some test or problem. This you can show. Okay. Now you can see that limit of biggest and smallest limit of f dashed is guarding the biggest and smallest limit of f by g, is guarding it, right? Which means that if limit of f dashed and g dashed exist, once again we are re-establishing the same phenomena. When limit of f dashed by g dashed exists, which means when these two become equal, then that will make this inner thing also collapse and everything becomes equal. And that implies limit of fx by gx also exists and they are all four equal. So that will imply L'Hopital's rule, but this is much more than that. Okay, I shouldn't say much more, but it is more than that. Okay, so this is the thing. Yeah, let us stop here. Let me not get into the definitions today. We'll do that next time, or not next time also. We'll do that later. Okay, next time we will see other applications of Cauchy mean value theorem, like maybe Taylor's theorem and so on. Okay? But we'll bring it in a natural, gradual way. Okay, so are there any questions? Today we have a long class because we had a class after very long, so it's okay. Again, you can just take a few minutes. I'll wait. If you have any questions, you can ask about what we have done so far. And this is just, I am trying to frame things in this because these results are there throughout. Root test, ratio test, there is a similar thing. Basically, the phenomena is that whenever you have this one-side implications about something and it comes through equations, then the equations don't know analysis, right? So if you loosen your analysis through the equations, you can still extract these things because these things are not a coincidence, right? So there'll usually be some structure. And this is the more hidden structure. Yeah, there should be much more about these things which I don't know. Yeah, but it's not about knowing. I mean, if you understand and discover and then ask and find and so on. Okay, so there are no questions? Okay, okay. So I've recorded this so you can see it again if you need to, means obviously parts of it or whatever. And you can ask me later because maybe we did some new things today. So yeah, and please do the counterexamples and so on, which I've asked in between. Yeah, fill in the gaps, fill in the things where I've asked some limit exists, something I've just written. Try to fill it in, write it. That's the practice. Yeah. Yeah, and before I leave, I'll just give you another problem that you can try. Okay, and I will not motivate this problem and so on now. I'll just give the problem. Let me just frame it like this. Okay, leave it. I have to frame it. Leave it. We'll do it next time. Okay. Yeah, and some questions some